Good evening. Today, my name is Chris, and I'll be discussing the importance of linear algebra in real life. We'll be testing its importance by exploring two real-world applications of linear algebra. First off, a core component of linear algebra are matrices. Matrices are essentially an array of numbers. Matrices, they have to be rectangular though. So, in other words, there must be the same number of elements in each row. And matrices can have any number of rows and columns. We'll often denote a random matrix by m by n, or n times n in notation. And this denotes that there are m rows, and n denotes that there are n columns. So these can be useful when determining systems, when solving systems of linear equations. You can determine m and n by the number of variables or the number of equations. So what exactly can matrices be used for in real life? Well, we'll start in physics. So in physics, you might have learned about moment of inertia, denoted by I. And moment of inertia is often abbreviated as MOI occasionally, but we'll use that to simplify writing. And the inertia is an important property of a tool, of an object. It measures its ability to resist rotation. In other words, if the moment of inertia is greater, then it will resist rotation greater, assuming that a same force is applied to it. So we'll explore inertia, and inertia can be represented by a matrix. So specifically a 2 by 2 matrix. So what is the inertia matrix? Well, we have the inertia matrix equal to, there are 4 entries in the 2 by 2 matrix, since 2 times 2 is equal to 4. Well, the 4 entries, the top left is Ixx, and the top right is Ixy. The bottom left is also Ixy, or it can be written by Iyx, but these are equal in quantity, as we'll explore later. And the bottom right quantity is Iyy. So how is this matrix useful? Well, we'll see. To calculate angular momentum, we'll need to multiply by a vector. A vector is often going to be angular velocity. Angular velocity is usually a vector quantity. And because it will have components along the x direction or y direction. So we can denote a angular momentum vector. We'll just give an example here, assuming there's only the x and y dimension, as a and b. So a and b are constant variables, and this a denotes that there is an angular velocity of a kilograms times meter per second, or somewhat that unit, along the x-axis, and b denotes that there are b units of angular momentum along the y-axis. So how is this useful to us? Well, we can actually get the angular momentum of L specifically with components using the equation L equals IW. Well, you might be thinking you can only multiply a constant here by a vector here to get the angular momentum. Well, you can actually make I more complex, and this multiplication will still work. If I is just a 1 by 1 scalar, L will still be a 2-dimensional vector, and if I is a 2 by 2 matrix, L will still be a 2-dimensional vector. So the usefulness of this applies to calculate the moment of inertia matrix is to calculate angular momentum. So what do these values represent? Well, Ixx is equal to the moment of inertia about the x-axis, and this can be calculated with an integral, x squared times dm, which are just represent little masses. And similarly, Iyy is the moment of inertia about the y-axis, which is equal to y squared integral of y squared dm. Now, you might be wondering what the Ixy term is. The Ixy term here, it represents how the symmetric distribution of the mass with respect to either axis. In other words, it represents how symmetric or asymmetric the object's mass is distributed relative to either the x-axis or y-axis. If Ixy is equal to 0, then the object is either symmetric about the x-axis, y-axis, or both. But if Ixy is not equal to 0, but rather equals a pretty big number, a big magnitude of number, like 50 or etc., that means that there is a high degree of asymmetry. We'll explore what this means when an angular velocity is present. So when Ixy equals 0, where there's a high degree of symmetry, usually physicians like to set the axes such that I of xy equals 0. This can come from rotation of axes, but we'll get into that in another lesson. So if Ixy equals 0, then Iyx also equals 0. And you might be wondering how we calculate these two quantities. Well, it's just equal to xy dm. You might not be familiar with the moment of inertia of this, but you can see if the mass is distributed symmetrically with respect to either the x-axis or the y-axis, all the integrals of the dm's will sum up to 0, and we just get Ixy equals 0. So what does this term actually represent? Well, it represents rotation coupling. In other words, assuming that there is an angular velocity along the x component, then that means it will not cause an angular velocity component along the y component. In other words, the x and y axes function independently of each other. I'll give an example calculation here. For instance, let's assume that Ixy equals 0 for a random fit object, and then we will just make up the Ixx quantity as equal to 5 and the Iyy as equal to 4. So we'll do some sample calculations here. So then we get the moment of inertia matrix is equal to 5, 0, 0, 4. And now let's assume there is an angular velocity component only directed along the x-axis. We'll just assume it to be 8 units. And then we get L will equal to 8, 5, 0, plus 0, 0, 4. And if you do vector operations, you get that this L is equal to 40, 0. So we see here that if there is an angular velocity only along the x component, then there will only be an angular momentum vector quantity only about the x component. The angular velocity component of the y will remain equal to 0. Of course, we can also set y equal to the y component of angular velocity equal to a random variable. We'll just call it n. If we call it n, then when we multiply these, we replace this with n, and then this is still 4, and we get that the angular velocity component about the y-axis is equal to 4n, 40 plus 0 in the x component and 0 plus 4n in the y component. So in other words, we see that the x and y components function independently of each other, and they are pretty straightforward directed as well, because the x component of angular momentum will just be the top vector quantity times the Ixx component, and the bottom angular and the y component of angular velocity will just be the bottom component times Iyy. That's pretty straightforward, and they function independently of each other, and that's what physics objects we're familiar with. However, now let's do a calculation where Ixy doesn't equal 0. Let's assume that Ixy equals 7. This is just random and made up. And now let's assume Ixx still equals still equals 5, and Iyy equals 4. And now we can calculate the angular momentum vector. Once again, we have 5, ixx equals 5, ixy equals 7, ixy equals iyx equals 7, and iyy equals 4. And let's assume that the angular component along the x-axis is 8, and along the y-axis is 0. Now, if we do the calculations here, I'll box this up so it won't get confused with the other notes that I did. And if we do the calculation, it's 8, 5, 7 plus 0, 7, 4. This is equal to 40, 56. And why is this significant? So we see that there is an angular velocity component along the x-axis only, but we see that the angular momentum component is equal to 40 units along the x-axis and 56 units along the y-axis. So we see that when angular velocity is applied only about the x-axis, it will actually affect the y component of the angular momentum. So that means there's actually coupling between x and y. A rotation about the x-axis will cause a rotation about the y-axis and vice versa. And this is what happens when the mass is not symmetrically distributed with respect to each axis. So here is basically how linear algebra can be applied to when finding angular momentum, and a new way of interpreting what moment of inertia looks like. Thank you.